Hi, my name is Natalie Velez, and I will be presenting my research on observing transiting exoplanets with the Central Washington University 0.6-meter research telescope. This project was mentored by Dr. Cassandra Fallscheer and funded by the Ronald E. McNair program. The scope of this project was to observe exoplanets using the research telescope on campus. We chose 6 stars to observe between June 16th and July 22nd of 2021. The target stars chosen were Corot 2, Happy 18, Happy 23, Happy 67, Kepler 15, and Kepler 20. These stars were chosen because the exoplanets of these stars had a relatively short orbital period and transit duration, which increased the frequency of transits during our chosen observational time period, and thus increasing our chances of being able to see a transit. So, some background: a transit is when an exoplanet, which is a planet that is not in our solar system, crosses in front of its star from our perspective. In doing so, when we're looking at the star, it appears to dim in brightness because that planet is blocking some of the light that we would see. So that is illustrated in Figure 1 in the background section. You can see that as that planet crosses in front of the star, the light curve has a slight dip. So that is what we were looking for when collecting data of these 6 stars. So in order to do that, we took images of these 6 stars about every 15 minutes when they were visible in the night sky. And then using a few reference stars and a relationship between flux and magnitude, we were able to calculate the target star's apparent magnitude in each of the images. We then plotted this to create our 6 light curves. 3 of these light curves are shown here in the data section in Figure 2. Most of our light curves were pretty straight with no indication of any type of transit or major change in brightness. I would like to highlight our Kepler 15 light curve. There were a few instances of a pretty significant increase in brightness during the end of our observational period that definitely piqued our interest. We looked into this further and concluded that it did not occur because of a transit. The time that it would have taken Kepler 15's exoplanet to transit in front was a shorter time period than we were observing that night for, so we should have been able to see the decrease in brightness and then the increase in brightness, yet all our data is showing it's an increase in brightness. So we played around with the data and made a new light curve using a different method of linear regression, and we got a much straighter curve, which just further confirmed that this increase in brightness was not caused by a transit. So overall, we cannot confirm that any transits were observed during this experiment. At the moment, our most likely explanation for this would be that our telescope is not sensitive enough to detect the small dip in brightness that was caused during these exoplanet transits. Another explanation could be that we were not observing the stars during a time where their exoplanet was making a transit. However, this seems less likely because the reason we chose these exoplanets was their high frequency compared to the amount of time and nights we were observing. So if this project was continued in the future, if we choose exoplanets that have a large transit depth, that means we would see a much larger decrease in brightness during transit. It would increase our chances of our telescope being sensitive enough to detect and successfully observe a transit. Thank you so much for watching my presentation, and a huge thank you to Dr. Fallscheer and the McNair program for all of the support.